Okay, hello everyone. There's no one here right now. Hopefully some of you show up. We're going to go ahead and get started with some waves on a string and standing waves notes. And I'm going to kind of be popping between OneNote and my internet browser to use some animations and some simulations. All right, so first things first, when we're talking about waves on a string, I'm talking about waves created on like a literal string. It's not anything crazy like that. So we're going to specifically talk about the different properties that can determine wave speed and things like that. So this is a pretty typical setup of wanting to create a wave on a string. So on the left-hand side, we have what's called an oscillator, which essentially vibrates that end of the string up and down to create the wave. Because remember, waves are created by some type of oscillation or vibration. And when we're creating these waves, we're going to be creating transverse waves. So we're going to be sending transverse waves down the string where the energy is traveling essentially horizontally, but the individual particles are just bobbing up and down. Okay, so that oscillator is really useful because we can vary the frequency that the oscillator bobs up and down at, which can vary the frequency of the wave created. Okay, now the waves on the string are still going to follow the V equals F lambda equation. That part still holds true. So as we vary the frequency of the oscillator, the wavelength of that wave is also going to change. Okay, now we also talked about on Monday how the medium that the wave travels through can change the speed of the wave. So that's what we're going to kind of talk about today, is the second half of the equation. Now this equation isn't on your reference table, and if we were going to test this on the AP exam, it would be given to you. But it basically says that the speed of the wave on the string is the square root of the tension in the string divided by the mass density, or essentially the mass of the string over the length. Okay. Now, even though we might change the length of the string, the mass density of the string, or how much mass is in a specific length, only changes if the string changes. Okay, so as long as we're dealing, as long as we're dealing with the same string, we should have the same bottom part. Okay. Now that tension in the string can either come from a hanging mass like I have pictured, or it can come from tying this end of the string here to a rod, and we can vary, how tight we tie that string. Okay. Now, if we are using a mass on a string like I have pictured, this mass here is actually going to remain at rest. Yes, it'll bob up and down a little bit just as energy is transferred through the string, but it's not going to be accelerating in our normal sense. So what that means is the net force acting on that box is 0, which means that any upward tension force in that string has to equal any downward force of gravity. So that tells us that the tension in this horizontal section is actually equal to the force of gravity on the mass. So if we change the mass of the hanging mass, we're going to change that tension. And they have a square root relationship with the velocity. Okay. So what I'm going to do now is hop on over to a simulation to help us kind of look at how varying the oscillator's frequency can change the wavelength, and how changing the tension can change the speed. And we'll also look at how maybe changing the amplitude, is that going to affect the speed or anything like that. So what you can do to get to this is you can Google FET waves on a string, and the settings that we're going to take part in is we're going to do oscillate, and we're going to do no end. So I'm just going to restart that. Okay, we're going to set damping, which is essentially like wave friction, to none. Okay. And let's go in slow motion, because why not? All right, so the speed of the wave that we're going to want to look at is actually the speed of one of the crests traveling across the surface. So we want to see, okay, let's measure. You can't really see where I'm pointing, and I wish I had like a laser pointer. Let's see, does this have, no. I don't have like a laser pointer. I don't know if you can see the cursor, but we're measuring like this traveling. So like this, that's the speed that we're looking at. And we could actually like measure that speed using rulers and timers and things like that. So let's get rid of those. So first thing I want to look at is the amplitude going to affect that speed? So let me just make the amplitude like really, really, really small. Okay, maybe that's a little bit too small. Let me make it a little bit bigger. Okay. Well, let's see. Let me make that a little bit bigger. So it was at 0.75 before. And honestly, that speed, I'm just like following it with my finger, and that speed looks pretty much the same. So let's actually do some data collection. So let's say we're measuring the time it takes. Oh boy, this is going to be fun. So I'm going to put this here, and we're going to follow a crest or a trough. No, let's follow crest. So crest, I'm following it until it gets to the door. Boop. So about a second. Remember, this is in slow motion. Okay, so now let's make the amplitude as big as it'll go. And we'll still see if it'll take about a second. So again, I'm going to measure the time it takes a crest to get from this beginning part to the door. So I'm going to start now. Hope I probably should have reset it. That would have been good. So again, I'm going to start now. Nope, it would be good if I hit play. Now. Yep, so still about a second. So amplitude isn't going to affect the speed of the wave. It just affects the amount of energy of the wave. So remember, keep that in mind. Okay, so now let's change the tension, which we know from the equation that we just talked about, this one up here. Changing the tension should change the speed. Okay, so let's go ahead and remember our current speed is about a second. So let's go ahead and go to low tension. Well, I mean, I can already see that this wave is moving pretty slow, and I'm guessing it would take a lot longer for a crest, meaning one of these top parts, to get to the door. So let's just go ahead and follow on. So I'm following this, again, I don't know if you can see it, this one right here. Well, we're already at greater than a second, so it's pretty clear that the speed of our wave has changed. We've decreased the tension, we've decreased the speed, meaning it takes a longer amount of time to travel the same distance. Okay. So the other thing in this simulation that is in the speed equation is frequency. Now you might be thinking, oh, well, if I change the frequency because, you know, v equals f lambda, shouldn't that change something about the wavelength? So let's go ahead and see that. So I'm going to go ahead and increase. I'm going to set this back to high because we know that speed is about a second. So I'm going to go ahead and go like that. All right, so we have a higher frequency. Now you'll notice that there are more waves now that we see. Higher frequency means more waves in the same amount of time. So let's go ahead and follow a crest again and see if we've affected the speed at all by changing that frequency. So there, I'm following this. And I'm still getting about a second. So even though we've changed the frequency and looking at our equation, maybe that should change the speed. Frequency isn't going to change the speed. The reason why is because as you change, like we increased this frequency, but what we did in addition to increasing that frequency is we actually decreased that wavelength, which kept this speed the same. So the only way to really change the speed of a wave on a string is to change something about the string, meaning change the tension or change what the string is made out of. Okay, so again, the only things that are going to affect the speed is the mediums that we're traveling through. So in this case, the tension or the type of string. Changing the frequency is just going to inversely change the wavelength, keeping the speed the same, and changing the amplitude isn't going to have any effect. Okay, so now let's talk about standing waves. And we're going to talk about standing waves on strings. We'll talk about standing sound waves probably on Friday. Okay, but now we're going to talk about standing waves on strings. So why do we consider them to be standing waves? Like, what does it mean to have a standing waves? Well, what we were just seeing is we were able to see very clearly the energy of the wave kind of traveling across the screen. So when we have a standing wave, that energy of the wave appears to just kind of stand still. Okay, so that's why we call them standing waves. So it's not like standing straight up. It's like when you see a sign in your car and it says like no standing, it essentially means like no stopping, right? It's the same thing for a standing wave. It just appears that they have stopped. Okay, now some of the particles are still going to move, okay, but instead of the energy traveling left or right, it really just appears to stand still. Okay, so these are created when a wave is sent down a string, reflects off of a fixed boundary, that wave inverts and then interferes with itself. And that interference is always going to occur no matter what. So anytime we send a wave down a string, like, let me just go like that. Like anytime we send a wave down this, we're going to have some sort of weird interference pattern going on, but it's not going to be considered a standing wave or a true standing wave until we get to a very specific set of frequencies. Okay, and this is because only parts of the wavelength are going to be able to stand on the string, so to speak. Okay, so what's actually happening in a standing wave is, here's kind of a really nice animation. So the blue wave is probably the original wave that's being sent down whatever wave. The red wave represents the reflected wave, and then this black wave, which appears to stand still and just kind of oscillate or bob up and down, is the interference of those two waves. Okay, so this black wave is what you'd actually see. The red and the blue are just kind of what's going on underneath. So let me go back to this. Let me restart it. Okay, let me go in slow motion. Okay, so watch what happens. We send the wave down. Let me do a slightly larger amplitude. It'd be easier if I just slip. So we send the wave down. Okay, here's our original wave. Now we're still creating that wave. So as that wave reflects, it starts to interfere with the wave that's being sent down. Okay, so it's essentially like if you sent a line of people at a wall. Once they get to the wall, they're going to turn around, and those people are now going to interact with the people that are originally in the line, and there's just a lot of interaction. And you know, sometimes you get such interference that the waves cancel and then it starts over again. Okay, so those are standing waves and interference. Now, like I said, standing waves can only be created at specific frequencies because only parts of the wavelength are able to stand, so to speak, on the string. So what does that look like? Well, this is when we start to talk about, and it's frozen a little bit. Come on, computer, you can do it. I just need one note to work. There we go. Okay, so this is when we start to talk about harmonics. Okay, so when we talk about harmonics, we're talking same string length, same tension, which means we have the same speed. Okay, so this first drawing here is the first harmonic, or the fundamental frequency, or the fundamental harmonic. It has a couple of different names. Okay, but in this, the wave, the standing wave, is going to appear to oscillate between the green and the black line. So the green and the black line are not occurring at the same time. It's just oscillating between that. Okay, and so on that standing wave, we have half a wavelength. So let me show you what that looks like in an animation. I gotta get to specific. All right. Let's go normal speed. Okay, so it takes a little bit, but you can see that we're just kind of bobbing up and down between that half wavelength. So the end over here is at rest, and then the end over here is pretty much at rest where the wave is created. And we have this nice broad center section. So this is called the fundamental frequency, or the first frequency where a true standing wave can be created. Okay. So a lot of the times the questions that are going to be asked are going to be like, okay, well, if you're presented with the picture, what's the wavelength? So in this case, we have half of a wave. So we have half of a wave in a length, a string length L. Okay, now we can set up a proportion to figure out what the actual wavelength is. Okay, so the proportion that I'm looking at is this here. So we have 1/2 of a wave in L, so that means we'd get one wave in X. From there, I cross multiply, and I see that my wavelength at this frequency would be 2L. Okay, so the speed I could calculate if I knew those variables by using V equals F lambda. The fundamental frequency is considered F0, so I can say F0 times 2L and rearrange it just to make it look like, so my speed would be 2F0L. And that speed is going to remain the same no matter what frequency we put on the string. We just saw that in the previous animation, that no matter what, the frequency isn't going to change the speed, the frequency just changes the wavelength. Okay, so now let's say our picture, or what we're presented with, is this. Okay, well, this is one wavelength, right? One sine wave. So that means our wavelength, or lambda value, is L. So our speed is just whatever frequency this occurs at times L. Now, let's say we wanted to know if there was a pattern that would emerge between the fundamental frequency and the other later harmonics. Like this would be considered the second harmonic. Well, I know that this speed, right, this speed here and this speed equation appear the same. The speed's going to stay the same. I haven't changed anything about the string. So that's why I went in the next step, plugged in 2F0L. Now the L's cancel because the length of the string is the same. So that means that this second harmonic frequency should be double the original frequency. So let's go ahead and see if that's true. So here I was able to create a fundamental frequency at 0.4 hertz. So that means I should be able to get the second harmonic at 0.8 hertz. So let's go ahead and see if 0.8 hertz gives me that nice. I'm going to pause this, and we should be able to see one full wavelength. So let's see. Fingers crossed. All right. So we're going to let it go for a little bit. Now what's happening now is the amplitudes are essentially adding together, creating more and more energy because the waves are reflecting off of both ends now. So we just have lots of amplitudes adding together. And it looks like we have a pretty stable standing wave in the second harmonic. So our second harmonic is double the fundamental frequency. Awesome. Let's see if that pattern continues. Does the third harmonic give us 3 times? Well, the third harmonic would represent 1.5 waves. So you see, we're adding half of a wavelength every time. Now, the reason we have to do that is because the ends of the wave have to be those like pinch parts, essentially. They have to be those non-moving parts. So at the third harmonic, we have 1.5. OneNote's kind of freaking out. At the third harmonic, we have 1.5 waves. So 1.5 waves over L, we can use a proportion again because it's not as straightforward as the last one, is going to equal 1 wave over X. So I cross multiply and do some division, and I see that, oh my goodness gracious, and I see that X, or my wavelength, is 2/3 L. So that should make sense, right? We have 3/3, right? We're essentially set up into, we've broken it up into thirds, and one full wavelength occurs in 2 of those thirds. Makes sense. So again, I can use the same type of reasoning that I did before. V is the frequency of that third harmonic times the wavelength, which is now 2/3 L. The speed is still 2F0L. It's always going to be that until we change something about the string. So I do that. I can cancel out 2s. I can cancel out L's. And I end up getting that the frequency of this third harmonic should be 3f0. So I should be able to increase this to 1.2. We're going to restart it. And I should be able to see that nice 1.5 wavelength getting stable, and I do. And the longer this runs, the larger the amplitudes will get, obviously, until we like reach the stretch point of the string. Okay, so that pattern continues on, right? So here we have 2 wavelengths, which means that our 1 wavelength, right, would equal L over 2, which makes sense. We have 1 wavelength and half of the L. And our frequency here should be 4f0. So let me add, so I should be able to throw this up to 0.6. And I should be able to get 2 wavelengths. Bloop, 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 which I do. Yay. It's exciting when things work out. Okay. So again, we see a pattern emerging with these harmonics. So kind of shortcut for this, and some of the con questions will kind of ask about this, is if you know the frequency, the original fundamental frequency, you can find any other frequency for the harmonics by just multiplying by the harmonic number. And the harmonic number is essentially the number of what I'm going to later describe as antinodes. So there's 1 antinode here, so it's the first harmonic. 2 antinodes here, so it's the second harmonic. And I'll explain in a second what an antinode is. Okay. So we can multiply the original frequency by any integer and get another frequency where a standing wave can be found. And we can use the fact that the speed remains the same and the length of the string remains the same to find wavelengths and things like that. Okay, so anatomy of a standing wave. There are specific parts on a standing wave that we sometimes get questions about. Okay, so I labeled them with black dots and green X's. So the black dots, which are always going to occur at the ends here, and the kind of center line parts here, those are considered nodes. So that's where the 2 waves that are interfering with one another are going to be destructively interfering. And they're actually going to be completely destructively interfering, so they cancel each other out at those specific locations. And this is where the waves are considered 180 degrees apart. So what does 180 degrees apart mean? It means that, right? Where the incoming wave looks like that and the reflected wave looks like that. They're essentially opposites of each other. Okay, so in these areas, the particles do not move. So I like to think nodes are where there is no motion. Nodes, no motion. Nodes, no motion. Okay. And then we have the green X's, which represent, like I had said before, antinodes. So these are where the 2 waves are constructively interfering. So they're considered to be 0 degrees out of phase. So they both look exactly the same. So if this is the incoming wave and this is the reflected wave, those 2 things would combine to give us an antinode. Okay. So this is where the most vertical motion of a particle is going to occur, right? Where they have the most maximum velocity. They're flipping up and down, up and down, up and down, up and down. Okay. Now, one thing a lot of students do is they'll accidentally incorrectly count the antinode. They'll count 1, 2, 3, 4, 5, 6, 7, 8. There's not 8 antinodes here. There's only 4. There's 4 areas of maximum amplitude. Okay. Whereas there are 5 areas of no motion. Okay. So just make sure if you're asked to count the number of antinodes or nodes, you're doing it correctly. And remember, the number of antinodes for this type of problem also gives you the harmonic number, which also gives you the n value for what you would need to find the frequency, right? All right. Okay. If you did want to play around with PhET, with standing waves, you can set everything to oscillate, fixed end, no damping, high tension, and your fundamental frequency should occur at around 0.4 hertz if you want to like play with it. All right. And that's pretty much it for standing waves on strings and waves on strings in general. You'll have some Khan Academies dealing with this stuff, I think tomorrow and Monday. Yeah. On Friday, we're going to talk about standing waves for sound waves. Now, those are going to look a little bit different, and they're a little bit more complicated because remember, sound waves are longitudinal waves, so there's those like compression areas. All right. But that is it for this presentation. No one's here, so I don't think anybody has any questions, and I will see you guys maybe next week when you come to drop off textbooks and stuff. All right, bye.